Good afternoon and welcome to this Isaac Physics online tutorial on problem solving using vectors. This is a follow-up to our workshop that we've been running around the country. So if you haven't been to one of those workshops, I'm afraid that you won't be able to follow along because it requires the sheets that you got there. I'm Michael Quinterio. I work for the Isaac Physics project and I'm going to be your tutor for today. And during this tutorial, you'll be able to ask me questions using the box, which you should be able to see below this video on the Isaac Physics website. If you're not there, go to isaacphysics.org, click on events, and then you should be able to find this event being live there. And you'll be able to log in and send me a message using that. If you are watching, please do send me a message. No, pardon me. Please do send me a message so that I can know who's listening, who's watching. And if you have any particular questions about any aspect of the Vectors workshop, stick them in there and I will read them and I'll be able to cover your specific point and cover what you're confused by. There is a slight delay in me receiving the messages from that box, so don't worry if you're confused about something that I've said and I appeared to have just ignored you and carried on. It just means I haven't got your message yet, and I will come back and take that into account and go over the bit that's been confusing you. So during this, I am going to be sharing my work screen with you so that you can see what I'm doing. So if I just move that over now, there we go. Okay, so what we're going to do is we are going to start looking at some of the later questions in the Vectors workshop, ones that you probably didn't get around to actually finishing during the workshop. And again, if they've got any particular question parts you'd like me to cover, please do use the box below and send me a message. So I'm going to start with exercise 8. It says, cosmic rays are charged particles that move randomly in a galaxy as a result of being scattered by randomly oriented interstellar magnetic fields. This process resembles diffusion. In such situations, we can apply a random warp to the cosmic rays reaching the Earth from beyond our galaxy. Given the dimension of our galaxy is 5 times 10 to the 20 meters, and if the mean free path for a cosmic ray is 3 times 10 to the 18 meters, estimate how long it takes for a cosmic ray to travel across the galaxy, assuming that it travels at almost the speed of light. So what we need doing is, with most physics questions, it's good to have a diagram that will enable us to kind of condense all of our thoughts into a single image with notes, and crucially, we're going to try and use symbols for as much as possible rather than putting in actual numeric values. So if we imagine our cosmic ray bouncing around the place, and eventually traveling a distance, capital R, which is going to be the dimension of the galaxy, and all of the distance that is traveled through that, I'm going to say is length L, and it's made up of lots of little bits which have an average length lowercase a, which is going to be our mean free path. So R equals dimension of galaxy, L equals total distance traveled, which is obviously much bigger than R, and A equals mean free path, and N, capital N, I'm going to say, is the number of steps. Now, this means that RL, total length traveled, is equal to the number of steps multiplied by mean free path, and I'm going to call that one equation 1. Now we go back to our exercise, and so the process resembles diffusion, and we've got a random walk. And from the work that we did inside the workshops that we held, we found that the distance traveled away from the start point, so from here to here, which is r in this case, the average distance traveled is equal to the root of the number of steps multiplied by the length of a step. I'm going to call that equation number 2. And what we're trying to find is the time taken. And we've got, so the time taken, t, which we're trying to find, is equal to the distance traveled, the total distance, which is L, not R, divided by c, the speed of light, which is the speed of our cosmic rays. And so we can substitute 1 into 3, which gets us our new equation, t, wrong color, t equals n a over c. But again, we don't know what this capital N is. But what we can do is we can look at 2 and we can rearrange 2 to find N. So squaring both sides, r squared equals n a squared. So n equals r squared divided by a squared. We'll call that one equation 5. And then substitute our equation 5 into equation 4. So we have t equals n r squared over a squared times by a divided by c. So we get r squared over a c, which is our answer. Which, when you put the numbers in, will give us our answer. Okay, moving on from there, we're going to look more at some things where adding vectors. So we're going to move to exercise 9, which states that the vector capital R is formed by adding the x components and the y components of the Ri vectors whose orientations are random. So we've got R made from adding x and y components of random Ri, and that's just the same as R made from adding these vectors, because we're adding together our 2 components which are perpendicular. So that's just the same as adding the vector. Okay, part A. If one of the lowercase ri is projected onto a particular axis, explain why on average the projected value is 0. So we can define whatever axis that we want. So I'm going to say this axis. And if we now draw our ri in, then this would be the projection. But the thing is, this ri could be anywhere, and so we have to find the average of all the different ri's, the projections onto this axis. And the thing is, for each one like this, there is another one, ri, which has a projection here. And so let's say this is plus y1, this would be minus y1. And so the average of those 2, the projections, would be 0. And it's the same no matter where we draw on here. So we know that the average projection must be 0. That's A. Part B, what is the average value of R? And we can think of this in terms of different components. So let's think about the average component of R in the x direction, which is sum of all these Ri's which make it dotted with our x component. Average. But this has to average to 0 because we just said the average projection of on every axis equals 0. We also must have the average Ry equals 0 and also the average Rz. So therefore, our average overall vector is 0 in the x direction, 0 in the y direction, and 0 in the z direction. So it becomes the 0 vector. But then we're looking in part C for, actually I'm going to take some more, get rid of all this, so I've got some more space for the next one. So part C, show that R squared, and this is the average size of the vector R. And so the average vector R is 0, but the average size is not 0, because if you imagine beforehand, we're looking at, let's just draw R. And so for R, like no matter where you end up, oops, you have a vector R, you will have equal chance of another vector in the opposite, that's not quite in the opposite direction. So the average of these two vectors is 0, but the average size of these two vectors is not. What we're actually trying to find out is R squared, which is the same as this R vector dotted with itself, dot product of capital R and capital R, the two vectors. And we get different sorts of terms. We get things like R1 dot R1. So all of, actually, let me write this out so I can make it a bit clearer. So we've got R1 plus R2, all of these components making it up all the way up to Rn, dotted with the same thing again. So obviously we've got terms where we've got things like R1 dotted with R1, R2 dotted with R2, and so on and so forth. We've also got lots of terms which are things like R1 dotted with R2, R1 dotted with R3, R1 dotted with Rn, and so on and so forth. So all of these, any vector dotted around itself, well, that's just the length of it squared. So we're going to call that lowercase r squared, lowercase r squared, and so on and so forth for those. And because these are random, on average, these will all come to 0 because we've got R1 dotted with all these other random vectors. And from before, we found that the random vectors, their projection on any axis is 0. And this time we're taking R1 to be our axis. And of course, the same thing happens with R2 and R3. So these all sum to 0, which means in total we have n, which is our number, this little case n here, times r squared. Okay, so I am going to move on from here now. I'm going to skip ahead a bit. So let me get rid of that. And I'm going to go on to looking at some projectile questions. This is an additional questions section starting on page 9. And it has a little description of our projectiles. If a velocity changes and you can recognize that an acceleration has occurred and deduce that a force has been acting. In the case of a body being thrown horizontally while also being pulled by gravity towards the ground, there is no force in the horizontal direction, ignoring air resistance. While in the vertical direction, there is a force which produces a constant acceleration downwards, again ignoring air resistance. The motions horizontally and vertically are therefore found to be independent of each other. So that means that so long as we resolve everything into all of our vectors into two different vectors, horizontally and vertically, we can just completely separate out those two bits of motion. Start with exercise 10. A projectile is fired horizontally off a table at 4 meters per second. It falls towards the ground with an acceleration of 10 meters per second. So the first thing that I'm going to do is I'm going to pick my positive directions for this, just to make things easier. And I'm going to say to the right is my positive x direction and down is my positive y direction. And we have positive acceleration down given by g, which in this case we're told to take as 10 meters per second squared. But I'm going to leave it in symbols for now. Says also time equals 0. We have our velocity 0, which is horizontal. Calculate the magnitude and the velocity at times t equals 1, 2, 3, and 4 seconds. So I'm going to, in fact, just call these t1, t2, t3, and t4. And so we know that horizontally there is no acceleration. The only acceleration we've got is down with an acceleration g. So in all of these, we're going to have a horizontal component of the same length as the initial velocity. Okay, right, using we start off with 0 vertical velocity, so we can say all times v vertical is equal to this acceleration times by the time. So if I draw here, we've got gt1, gt2, gt3, gt4. And now we can add together those components in all of these cases. Oh, that gt4 is awful. That needs to come down much further. What happens when I don't take my time and get sloppy with my drawings? There we go. And so those are our velocities. And in all of these, we've got right angled triangles. And we can call these angles theta 1, theta 2, theta 3, theta 4. And we can work out the magnitude of the velocities using Pythagoras' theorem. And we can work out these angles to the horizontal using trigonometry. And if we wanted to think about the path of this, so in all of these, they should be separated horizontally by the same distance. I'm not drawing it very well, but the velocity is tangential to the path. Okay, and I'm finally going to finish off with exercise 11. So let's hide this. Exercise 11 says, 2 projectiles are fired horizontally in opposite directions at 3 meters per second and 4 meters per second. At what time are they passed at 90 degrees to each other and how far have they fallen? This can be done by sketching the diagram of the vectors and algebraically using the vector notation and vector dot product discussed in the concept sheets that you were given before the workshop. So let's look at drawing the diagrams of the vectors. So we're going to have, so initially we have UA and UB. So they're in opposite directions, and you can put the magnitudes in yourself. And then, oops. So that's initially. After time t. And remembering, we've got an acceleration downwards of g, and also going to label these directions as positive in x and y. We're going to have our VA and VB. Angle. We've also got right angles here and here. And we said that there's no acceleration horizontally. So in fact, this here, this component has a magnitude of UA. And this horizontal component here has a magnitude of UB. So then we've got a Pythagorean triangle where the sides are VA and VB, and the hypotenuse is UA plus UB. But for each of these, we treat them separately. So we've got a right angle here. So we got VA. This is UA. And our vertical component is GT. And so from these, the individual ones, we can get VA squared and VB squared from thinking about individual vectors. And then we can put that back into here and then solve for our t. Then from how far they've fallen, we've just got looking vertically. B is UVT, that's a half A B t squared. So these are vertical initial speed and vertical acceleration. Well, initially there was no vertical speed, so that first term is 0. And our vertical acceleration in the positive direction is g. So once you've got your t from solving up here, you can pop it in here and find out the distance that has fallen, the distance that the projectile has fallen as well. Now, just to finish off, we can do this algebraically using the vector notation. So we had our UA, UB, and if I write them vectorially, I can say UA is equal to, let me define positive directions again, just as a reminder, x and y. So in x direction, we have UA, and in the y direction, 0. And so here you should be able to see that I'm distinguishing between the vectors, which are these underlined terms, and the components or magnitudes, which are not underlined, and the scalars. And then after time t, I'm going to have my VA and my VB. The horizontal components haven't changed magnitude, but both of these vertical components are GT because there has been a constant downwards acceleration, which is in positive direction of G. And so now I can write these two as VA equals UA GT. And I've just realized I'm stupid and I've forgotten to put the minus sign there. So easy to do, but it means complete different things because obviously this vector is in the negative x direction. So VB equals minus UB GT. And for our dot products, VA dot VB would give us the modulus of VA multiplied by the modulus of VB multiplied by cos theta, where cos theta is the angle between these two. So in fact, so the angle between these two, let me redraw them. So there's my VB, there's my VA. So for the angle between them, we need them both be coming from the same point, but we still have 90 degrees between them. Because 90 degrees is 0, which means that this is equal to 0. We can also write this in terms of the components. So we have our x components multiplied together, UA multiplied by U minus UV, and GT multiplied by GT for the y components multiplied together. So G squared T squared equals UA multiplied by UB. And then that should be simply enough to solve. So a lot easier using the vector notation. I hope that's been useful for you, and that you enjoyed that, as well as the Isaac Physics Vectors workshop that you attended. We'll be running more workshops over the year, and also I would recommend getting on isaacphysics.org, clicking on Have a Go, and selecting your own questions, so you can pick topics that you've done in school. So if you've just finished doing kinetics in physics, you can just ask for questions on that. Or if you'd like to push yourself, you can go for slightly higher levels. We say level 1 is basically end of GCSE. 2 and 3 are about first year of AS or first year of sixth form if you don't do AS. 4 and 5 are second year of sixth form or second year of A level, so A2. And 6 is if you really want to push yourself and start dealing with material which is beyond that, some of which will stump some of our university students. Remember, this will be live for a while. Do send us a message using the Contact Us form if you have any thoughts. And keep doing physics, and have a good evening. Bye-bye.